Hello, everyone, and welcome to this episode. Today, we are studying for the AP Chemistry exam, specifically looking at Unit 3, Intermolecular Forces and Properties. I'd like to start out by saying a couple things about this unit. First, there are 9 units in the AP Chemistry curriculum, and of the 9 units, this is the one we are told shows up the most often on an exam. While most of the other units are typically 7 to 9% of the exam, we're told that this unit is present 18 to 22% of the exam. So that's pretty significant, and I thought we should spend some time going through it. I would also like to say that this unit also doesn't really have much math associated with it. It's a lot of visual concepts and diagrams and models and words on the slides. So if at any point during the video you need to pause it and write anything down or look at the models that are on the slides, I tried to give you an example of each of the types of matter and each of the types of intermolecular forces. There's a lot here. You can see there are 13 subtopics. The first 3 are the most lengthy in terms of things we need to cover. And then after that, it's going to go a little bit quicker. So if it seems like it's dragging at the beginning, it's because it's top heavy in terms of some of the concepts. So let's get into it. We're going to start with intermolecular forces and work our way down through all of these topics and end with Beer-Lambert law at the end. Almost everything in this unit, from the properties of matter to the states of matter and the interactions between them, comes from intermolecular forces. And so that's where we begin our journey into Unit 3. And I'm starting with London dispersion forces, which are the weakest intermolecular forces for the most part. And I'm going to work my way to the strongest intermolecular forces as we go along. So London dispersion forces are the result of Coulombic attractions. Let's stop there for a moment and talk about this vocabulary. Coulombic attractions are attractions based on opposite charges, where something is either partially or all positive, or something is partially or all negative. And opposite charges will attract each other, and that's what we mean by Coulombic attractions. Between temporary dipoles, they are weakest in small molecules, but are often the strongest net intermolecular force between large molecules. So there, you got to imagine little electrons flying around inside of a atom or a molecule, and electrons, I like to say, are like little children. And if you set them out into a yard or a playground, they're going to run all over the place. And there is going to be some times where most of the children are off on this side, or most of the children are off on this side. And electrons are kind of like that. They move around through the molecule, and at any given moment, they might be evenly dispersed, so there's no imbalance, but they might all be over on one side of the molecule or the atom. And so you get a negative end of the atom or molecule, and the other end is positive. And so you have these momentary dipoles that can then interact with other momentary dipoles just for a brief instant of time, and then they go away. They're temporary, and they're fairly weak for the most part, although when you get to larger and larger molecules, their London dispersion forces, even though it's like technically the weakest one, in larger molecules, it can be really present and actually outweigh some more of the other stronger things like hydrogen bonding or dipole-dipole forces. They increase with increasing contact area between molecules and increasing polarizability of the molecules. More electrons, more polarizing action. And you have the number of electrons in the size of the electron cloud. It's also enhanced by pi bonding, which has those electrons in the pi orbitals. All right, continuing on. What about the dipole moment of a polar molecule can actually induce a dipole into a nonpolar molecule? I should go back and important to note that London dispersion forces are present in all molecules because all molecules and atoms have electrons, but they may be overshadowed by a stronger force at the same time. So if you're ever asked, list all intermolecular forces present in this molecule, you should always include London dispersion forces. You may not always include the other ones because they may not have them. So let's imagine if you have a little dipole, a little water molecule there, and it's polar and it has a negative end and a positive end. If that gets next to a nonpolar molecule, it can actually throw that other molecule out of balance, repelling its electrons and causing a temporary dipole to occur. And that's called a dipole-induced dipole interaction. These are always attractive, and they're typically a little bit stronger than London dispersion forces, although still on the weaker end of the molecular interactions. So take a look at that. I'm not going to read every word on every slide. Again, these are instructions given to us, and I'm trying to paraphrase. So let's do dipole-dipole forces. Whereas London dispersion forces are temporary, and they are fleeting, and they only last a short period of time for each one, dipole-dipole interactions are more permanent. They occur between molecules that are actually polar, like these two generic molecules here. And the interaction strength depends on the magnitudes of the dipoles and their relative orientation. They're typically greater than London dispersion for molecules of similar size because they act in addition to London dispersion, which occur in all molecules. So those are dipole-dipole forces. And your ability to recognize which intermolecular force a molecule has is dependent on your ability to tell if it's polar or not. Polar means it's asymmetrical. You have more electronegative things on one end than the other end, whereas nonpolar molecules are more symmetrical and they don't have electronegative atoms on one side or the other. So if you need to review polarity heading back to Unit 2, feel free to spend some time there as well. Continuing on with intermolecular forces, ion-dipole forces of attraction are present between ions and polar molecules. So this is included a little bit stronger than dipole-dipole forces. And we see these ions interacting, most of the time you'll see it with water, where the water molecules position themselves around the cation with their negative ends pointing in and the anion with the positive ends pointing in. And when ionic compounds dissolve in water, they do this. They don't actually float around independent of anything. They actually get a group of water molecules to hang out with, and then they float around. Sometimes the diagrams are simplified to not show these, but sometimes we are asked to show these. And so I would like to have you make a note of that. And we're told the relative strength and orientation dependence of dipole-dipole and ion-dipole interactions can be understood by considering the sign of the partial charges. So I'm including these examples just to show, yes, you're going to see these little signs of the partial charges, like a little lowercase delta minus delta plus, to show you in the molecule where the negative side is and where the positive side. These are not full charges, they're only partial charges, but you can kind of see where they are in the molecule. So that's an important notation to note. All right, and we get to everyone's favorite. Hydrogen bonding is a strong type of intermolecular attraction that exists in very specific cases. You have to have a hydrogen that is attached to an oxygen, nitrogen, or fluorine. These are the three most electronegative elements on the periodic table, and they're small, and they form these really highly polar bonds between the hydrogen and those three atoms. So you have to have the hydrogen attached to those three, not just in the same molecule, attached to one of those three. Like in water, you got two hydrogens attached to those oxygens. So it does these hydrogen bonds. It's a pretty strong attraction. The hydrogen is fairly positive. The other oxygen or the nitrogen or the fluorine would be very negative, and so there's a pretty strong attraction between them. They're kind of like dipole-dipole forces, except stronger. So they get their own category. And it's important also to note that in diagrams that you're going to see, the dotted lines represent the hydrogen bond, not the solid lines. The solid lines represent covalent bonds. Those are permanent unless a chemical reaction occurs. But the dotted lines, if you're looking for hydrogen bonds, look for the dotted lines. So I have another example of hydrogen bonding because we're told that in large biomolecules, non-covalent interactions like hydrogen bonding are pretty important in a lot of situations. So you might have, for example, in a strand of DNA, a couple of these building blocks, but they're held together not by covalent bonds, they're actually hydrogen bonding to each other, and those dotted lines represents the hydrogen bond. I've seen this question a lot where they'll point to different things in the molecule and say, which one represents a hydrogen bond? And they might point to a solid line or a double bond or whatever, and then you want to make sure, or they might even point to a hydrogen connected to a carbon, and that's tempting to choose that one. But you're really looking for the hydrogen attached to an oxygen, nitrogen, or fluorine, and those dotted lines between them. I want to continue here with two diagrams that I like to use in my classes, and they illustrate the idea of using intermolecular forces and their predictions to predict properties, macroscopic properties of different substances. And by macroscopic properties, I mean things like melting point, boiling point, viscosity, um, vapor pressure, enthalpy of vaporization, and so on. So things that we could measure of a collective group of atoms and molecules. So in general, the stronger the intermolecular force, the higher the boiling point, the higher the melting point, the higher the viscosity, but the one that goes lower is the vapor pressure. So the higher the intermolecular force, the lower the vapor pressure because the molecules are going to have a harder time escaping from each other and vaporizing. So that's a quick little summary. That's not all of them, but that's a quick summary. But in this one, they're showing us two groups of molecules. And the idea we're supposed to notice here is that they're very similar molar masses. So nitrogen and carbon monoxide are similar size atoms, molecules, and you get similar masses going on. So you might expect that because they're similar size, they might have the similar melting points and boiling points. Well, it turns out that over here, these boiling points are less than these boiling points. They're lower. So these molecules boil at a lower temperature. If I start heating at a low temperature and heat them up, these start vaporizing earlier than those, and the question becomes why. Well, we look at these. If we were to draw the Lewis structures for these, we would find that these are nonpolar molecules, whereas these are polar molecules. These would have London dispersion forces as their primary intermolecular force, whereas these would have dipole-dipole forces on top of London dispersion forces. So their attractions would be greater, their boiling points would be higher, and enthalpies of vaporization also a little bit higher because it takes more energy to separate them from each other. All right, and here is a popular graph. I've seen it many times in many versions. And what it's trying to show us is the effect of hydrogen bonding. And for example, you have nitrogen, hydrogen, and nitrogen, fluorine, and oxygen. Excuse me. And down here you have hydrogen attached to carbons. Now that one doesn't do hydrogen bonding. So if we were to make hydrogen-containing compounds with all of the group 4 elements, as they get heavier, their boiling points on this chart would go up because it just takes more energy to vaporize them. You also could go back down with, say, the group 6 elements, tellurium, selenium, sulfur. We're getting smaller and smaller compounds with similar shapes and geometries. And you would get to this point, and you might expect that water should have a boiling point somewhere down here to keep the trend going. But in fact, even though it's the lightest molecule of the group, its boiling point is way higher because of the hydrogen bonding that it exhibits. Same with hydrogen fluoride. We might expect hydrogen fluoride to boil down in here, but it actually boils at much higher, and same with ammonia. And again, it's just trying to show the effect of hydrogen bonding on their boiling points. Okay, that was unit subsection 1. Now we're in subsection 2, 3.2, properties of solids. There are several different kinds of solids you're going to need to know about, and I'm going to try to get through them with some diagrams to let you know what you should look for. Many properties of liquids and solids are determined by the strengths and types of intermolecular forces present. Because intermolecular forces are broken when a substance vaporizes, the vapor pressure and boiling point are directly related to the strength of those interactions. We saw that on a couple of previous slides. All right, this is where we get introduced to the Boltzmann distribution for molecules in a sample. Okay, and this kind of is a backdrop for the entire unit. Boltzmann distribution is a graph you're likely to see on the AP exam. I almost guarantee it. And it's one of those really important things, and it shows a distribution of molecular energies or molecular speeds. So, and it tells you the relative number of molecules that have that kind of energy. So in any given sample, some of the atoms have very low energy. They're not moving, they've kind of bumped into something else, and they're kind of hanging out, kind of sitting there for a second. Some molecules have a lot of energy. They've somehow gotten a bunch of energy from some collisions, and they're going really fast. Most of them are somewhere in the middle. And the peak of the distribution represents the average kinetic energy of that particular sample. And temperature is a measure of average kinetic energy. So if we were to heat up the sample, more molecules would have higher temperatures and less would have lower temperatures. The whole mountain would shift. The area under the curve stays the same, so it gets a little lower. So if you're ever asked to sketch one at a higher temperature, make sure you go farther to the right, but also make it shorter so it's not as tall as the other one, because you only have a limited number of molecules to make an area under the curve. But again, the average goes up when you have a higher temperature. Okay, so even though this little section is on solids, we are also introduced to vapor pressure. And here's a chart showing some vapor pressures of 3 different molecules. And if you look at them, you've got water here, which we know is very polar. Ethanol, which is kind of polar, it's got 1 hydrogen bond, whereas water has 2. And this one, diethyl ether, is fairly non-polar. That oxygen is kind of trapped in the middle there, not on one end or the other. And because it's non-polar, at any given temperature above minus 40, it's going to start vaporizing to a significant degree, whereas the other two go to a higher temperature before they start vaporizing. And it's not a linear trend. It gets more and more vaporizing as you go to a higher and higher temperature. And once you get, for example, water to 100 degrees, this is very, very important. This vapor pressure curve, we're vaporizing more and more and more and more and more. When we get to 100, something special happens. And it crosses this line that's at 760 torr, which is standard atmospheric pressure. So when water gets up to 100, its vapor pressure meets and exceeds atmospheric pressure that's pushing down on it, and that's what happens when something boils. It meets and exceeds the pressure of the gas pushing down on it from above. Ethanol gets there a little bit quicker at 78 degrees, and diethyl ether gets there at just under 35 degrees. So that's pretty important. I could spend all day talking about that, but we'll move on. Properties of solids. So they're telling us, okay, you're going to see some solids and you need to know about their particulate level representations. So I've included a few in here. Some that might include gases. Here's an element because all of them are the same, a diatomic element. Here's a mixture of different things. Here are those ions floating in the water with the water molecules around it. And then here's a solid. And that solid, we need to be able to identify what kind of solid that is showing us. And in this one, I see positive and negative things. And so that indicates to me that that's probably an ionic solid. Please note that the anions are always larger than the cations. Okay, when atoms lose electrons to become cations, they get smaller, and when atoms gain electrons to become anions, they get bigger. So when you're drawing an ionic compound, make sure you make your anions larger than your cations, because that will be worth a point, and you don't want to lose a point for something easy like that. All right, and speaking of ionic compounds, here's an example. We need to know the properties of ionic compounds as well. Once we've identified it, we may be asked questions about what are its properties. Will it have a high melting point or a low melting point? And due to strong interactions between ions, ionic solids tend to have low vapor pressures. They're not vaporizing much, high melting points, and high boiling points. They tend to be brittle because they have these zones in between the columns and rows, like little marchers. And if you get something between them, they pop off and tend to be very brittle like that. Especially if you take one layer and shove it down one notch. Now the anions are all next to each other and they repel each other and they break free. So that's an ionic solid. Next, we have network covalent solids. So these are made, graphite and diamond are two good examples you'll probably see. And they're made from nonmetals that are covalently bonded in a lot of directions, making a network. The bigger your network is, the more strong you are. And so diamond has properties that are like that it's very hard. It has very high melting points. It's really difficult to break all those covalent bonds and get them to melt. So when you're looking for something that has a super high melting point, it's likely to be a covalent solid, a network solid. Graphite is kind of an exception, as its layers of carbon atoms can slide past each other easily. So each of these layers, I don't know if you know, is called graphene. We've isolated graphene, and graphene is really cool because it has really wonderful properties, like it can conduct electricity and do some really weird things. It's also very strong lengthwise and widthwise, and it's only like a single atom thick, so it's like this really thin layer, but it's really strong in the tensile direction. It's actually fairly weak, though, between layers, because all they've got is some very weak attractions between the layers, which is why when you write with a pencil, you actually just using graphite and you just like rub it across the paper and little flakes of it come off. But each of those little flakes is actually very, very strong. So that's exciting. And molecular solids are next. We'll see this picture again. Molecular solids are covalently bonded groups of atoms, and they're attracted to each other by their intermolecular forces. They may be London dispersion forces, and the bigger the molecule gets, the bigger its LDF gets, the more tangled it can become. So it might have a higher melting point because of that. And some molecular solids do have dipole-dipole and hydrogen bonding. If you ever see like OHs sticking out of them and that kind of thing, but they will stack together by the nature of their intermolecular forces. All right, here's another diagram you're likely to see. And in this one, you'll notice that the round models in here are all positive, not like a positive, negative like in an ionic compound. So this is different, and this is a metallic solid. And you'll see the metallic solids only with the positive cores, which are kind of floating in a sea of electrons, where these electrons are always moving around, but they keep the sample together. All those cores are swimming in there, and the attractions keep them together. These have a wide range of melting points, believe it or not. Like mercury melts at like minus 39, whereas tungsten melts at like 3,000 degrees. So it's harder to tell melting point wise with metals because there's such a big range. But they are malleable and ductile, and they do conduct electricity. So that's some good things to remember about metals. And here we're introduced to alloys as well, which are mixtures of metals. These positive cores floating in a sea of electrons. Here the electrons are not shown. But we also need to know that there are two main kinds of alloys. One is a substitutional alloy, in which the atoms are swapped out for other atoms of similar size, and so they just kind of take the new spots in the lattice. Or interstitial, which are cool because you add a tiny atom in with a larger atom, and the tiny atom can actually take up that interstitial space in between the atoms, making the alloy much harder, such as carbon steel being harder than regular steel because the carbon atoms get in there and inhibit the movement of the bigger atoms. So that's exciting. Next, we have section 3.3, solids, liquids, and gases. So we're going to start here with solids can be crystalline, where the particles are arranged in regular three-dimensional layers, like in an ionic compound or maybe a metallic solid sometimes. But they could also be amorphous, where the particles have no regular pattern. They're kind of randomly dispersed. This is an example showing quartz, which is silicon dioxide, but that's been grown slowly over time, and so the atoms stack together nicely. Whereas glass is the same composition, but if you cool it down quick enough, the atoms just kind of join up to whoever's close, and you get this random arrangement. So crystalline versus amorphous. Okay, solids, liquids, and gases. Particles in a liquid are in close contact with each other, and they are continually moving and colliding. So it's important to visualize what the molecules are doing, and that may be the challenge for some of us in this unit. Some of us just want to have a math formula we can just solve for X and go. But here we're trying to imagine what atoms and molecules are doing. So there you go. These movements are influenced by the strength and nature of the intermolecular forces: polarity, hydrogen bonding, and temperature. And as you know, the temperature increases, the molecules start moving faster, and you might get to the point where a solid begins melting, turning into a liquid, and if the liquid gets to a certain point, it turns into a gas. And here we begin talking about gases. In the gas phase, particles are in constant motion and have significant distance between each other relative to their size. They're constantly colliding, and we're assuming that there are minimal effects of forces between molecules. Molecules are moving fast, and they're colliding with each other, elastic collisions. We're assuming for now that there's no intermolecular forces, but in reality, it actually do exist. And if you mess with the gas enough, you can actually get those intermolecular forces to play a part in what's going on. So imagine just molecules banging around in the gas phase. Here we get 3.4, the ideal gas law. And the ideal gas law you probably heard of and probably enjoy working with because it's a nice, easy equation, PV equals nRT. The pressure, this is for any gas under normal conditions, the pressure times its volume is equal to the number of moles, and the temperature times a constant, the ideal gas constant, which you'll find 3 different versions on your formula sheet. And that's a nice, easy equation. You may be asked to calculate something with it, in which case I'm hoping that you'll think, man, this is an easy point on the AP exam. But there are a couple of things that come out of it that I'd like to highlight. They're more conceptual, and you may be asked questions about it, probably more likely. Number one, under equal conditions of pressure and temperature, equal volume. So if we're keeping P, V, and T constant, and that's a constant, that means by extension that if you have equal volumes of gases under the same conditions of temperature and pressure, they contain the same number of moles. And that's a hard concept for some people to get because they look at samples of gas and they see a light gas and a heavy gas and a medium gas. Maybe there's a polar versus a non-polar gas. But it's really weird to think sometimes that balloon with tiny hydrogen atoms might contain the same number of atoms as much larger argon atoms, and so on. So they'll have different masses and densities, yes, because they're lighter and heavier atoms, but they will have the same number of moles and the same number of particles by extension from that. And also, we've learned that 1 mole of any gas at STP has a volume of 22.4, and that's useful to know. It's not on your equation sheet, I don't think. But if you're doing stoichiometry and you find moles of a gas and you want to change it into a volume, you can use the ideal gas law, sure. But if it's at STP, you can simply multiply by 22.4 and get a reasonable volume out of that. All right, under ideal gas law, we are also introduced to Dalton's law of partial pressures, which says that if you have one gas, it's got a pressure that's independent of any other gas. Those molecules will add pressure based on those molecules. And if you mix them with more molecules which have their own independent pressure and you put them together, you will simply add up the total of the two gases or three gases or whatever gases you have. They will add up to the sum of the partial pressures. So that's kind of nice. We may end up using that. And by extension from the ideal gas law, if you start keeping things constant, for example, if you keep the volume and the number of moles constant, we find that the pressure is proportional to the temperature. So you heat it up, pressure goes up. Similarly, if you keep the pressure in moles constant and you change the temperature goes up, the volume will go up proportionally. It's a linear relationship, and that's Charles' law. And here we have a graph of Boyle's law, which is kind of the other way around. As you decrease the volume of a gas, the pressure is going to go up. Or if you increase the volume, the pressure will go down in direct proportion, keeping, of course, the temperature and number of moles constant. So it's nice to have those. Those formulas are not written on the formula sheet. But if you know how to manipulate PV equals nRT, you can get to any one of them. 3.5, kinetic molecular theory. Again, we see the Boltzmann distribution. That's a hint that it's very important to all of us, but also the College Board. It's likely to be on the exam somewhere. And again, we have a low temperature, we have a higher temperature. The mountain is smushed a little bit, but flattened, and the area under the curve is the same, representing a higher temperature. Here's a quick little formula. The average kinetic energy of a particle is related to its average velocity by the equation kinetic energy equals 1/2 mv squared. Okay, let's talk about temperature and kinetic energy. And we'll actually go to the next slide and come back to this. The Kelvin temperature of a sample is proportional to the average kinetic energy of the particles in that sample. So it's important to note that if you have two samples or more samples and they're all at the same temperature, regardless of what they are, they will have the same average kinetic energy. And we were just doing a problem like this yesterday in class, and we were kind of wrestling with the ideas. The temperature was the same, and the question was, which substance has the highest kinetic energy? And they had different size molecules and things like that. So we had some guessing that the highest kinetic energy would be the lightest molecule or even the heaviest molecule. But they're actually all the same. And so kind of make a note of that because it's likely you're going to see it. But that said, for the same kinetic energy, different sized particles will actually have different speeds based on this equation. It's equal to 1/2 mass times velocity squared. So if you have a lighter mass for a given kinetic energy, you'll have a faster velocity. And if you have a bigger mass, you'll have a slower velocity. So that is good to note. We're starting to move a little faster through our sections here. Here are some deviations from ideal gas law. So that ideal gas law, it's great. And it's mostly like a really good suggestion. but it's not always true. And gases tend to deviate slightly from ideal gases, even under normal conditions, but particularly under extreme conditions. So it doesn't fully explain the actual behavior of gases, and here's why. They all have interparticle forces. So at any given moment, two particles might be colliding with each other and sticking together for a short time because they're attracted to each other. And that sticking together decreases the number of active gas particles in the sample. The pressure may drop because of that. And the higher the intermolecular force of the gas between the molecules, the more deviation you're going to get. Also, if you start cramming a bunch of molecules in here, the actual volume of the sample or the molecules becomes a significant fraction of the sample. And so we don't get this situation where the volume is just the total of a bunch of dimensionless little points. They actually start bumping into each other and affecting each other. So the biggest deviations from ideal gas law occur at low temperatures when the molecules are moving slow and they can attract each other. They kind of move by and then the traction. Whereas at a high temperature, they're flying by each other and they don't have a chance. Or high pressure when you get a bunch of them crammed into a small space. All right, we're going to do 3.7, mixtures and solutions. So solutions kind of take over the second part of the unit. And we are also calling them homogeneous mixtures of a solvent and a solute. And the macroscopic properties of a solution don't vary throughout the sample. If it was a heterogeneous mixture, maybe with some solid on the bottom or something like that, or some bubbles, your location within the mixture will dictate what you're going to see. But in a pure solution, you're going to have an even distribution of particles. Solution composition can be expressed in a variety of ways. Molarity is the most common method used in the laboratory. We used to have to deal with other things like molality and mass percent and mole fraction and things like that, but that's since been taken off the exam. So really focus on molarity as your unit of concentration, which is moles of solute per liter of solution. Representations of solutions. Particulate representations of solutions communicate their structure and properties of the solution. So again, you're probably going to see them. They also show the interaction between components. So you might see something like this, where maybe you're showing an acid and you have one hydronium, where you have another acid with a whole bunch of hydronium. So it's giving us information about how many hydroniums are in there or how many ions might be present. So whenever you see any of these, start counting the particles. I always tell my students, just start counting, because they're trying to maybe tell us something by the number of particles that are here. The more hydroniums, for example, the more acidic it is. Or the more solid particles in one, the more concentrated it is. So make a note of that. All right, so once we have things in solution, they're often kind of hard to separate because they have interactions with each other and they're all mixed together and things. We do have a couple of ways to do that are highlighted in this unit. One is mixture chromatography. So the components of a liquid can't be separated by filtration. They'll just everything go right through. They can, however, be separated by processes that take advantage of the differences in intermolecular forces between the components. All right, and chromatography you're likely to see sometimes. We do a paper chromatography lab, and we also borrow a gas chromatography setup every year. And chromatography there's a bunch of different versions of it, but they all deal with the same kind of properties. You have a mobile phase moving across a stationary phase. And the molecules in the mixture get picked up by the mobile phase and they travel across the stationary phase. But here's where it gets fun. Depending on the intermolecular forces of the molecules in the mixture, some may move faster across the stationary phase than the other ones. So for example, if water is my solvent and it's soaking up a piece of paper, some of the inks or chemicals that are soluble in water, maybe they're more polar, maybe they have hydrogen bonding, they'll be like, hey, the water's going up, let's go, let's move on up with it. Whereas other ones are more nonpolar and they don't interact with that mobile phase enough to make it up to the top. I do have a video about paper chromatography. I have it in the Unit 3 playlist if you'd like to check that out. for more detail on that. Another way we can separate mixtures, solutions, is by distilling them. And this is a fancier distilling apparatus, but if you've ever done a chemistry lab where you have like a salt solution and you evaporate it to dryness, you're just getting rid of the water and leaving the solid behind. That's a basic form of distillation. A fancy form of distillation is when you can vaporize it and then condense it into another container so you get a more relatively pure sample of whatever boiled at that temperature. Maybe it boils at 50 and you get something, and then maybe at 75 you get another thing. You can actually separate mixtures that way, which is kind of nice. We're already at 310. Things are speeding up. And here we're going to talk about solubility. To make a solution, you most of the time need to have things mixing that are kind of similar to each other. Not perfectly alike, but similar. Substances with similar intermolecular attractions tend to be miscible or soluble in one another. Like dissolves like is the cute little phrase we have. But like water will dissolve ions and things that are polar, because it's polar. And you've heard the phrase oil and water don't mix. That's because oil is made of nonpolar molecules, and the water doesn't want anything to do with them, and the nonpolar molecules can't get in there and interact with the water as much because the water is too busy interacting with itself. So that's a quick little phrase on that. In section 311 and 312, we take a little detour from intermolecular forces and states of matter to talk about how light interacts with molecules. And we call the study of this spectroscopy. And there's a bunch of forms of spectroscopy that you may encounter doing if you hang around the chem lab long enough. They might be visible UV spectroscopy, infrared spectroscopy, and so on. And each one is useful for different things. And here we're just kind of generally introduced to some of those. Microwave spectroscopy, if you shoot microwaves, and this is the thing about atoms and molecules, they contain electrons that are kind of like photons themselves. They have wave particle duality. They act like waves depending on the experiment you use to study them. And so electrons in atoms are able to interact with photons of light, and depending on the wavelength, they do different things. Also, the photons of light can affect and add energy to the molecule and cause it to vibrate or rotate or things like that. So, for example, microwaves, if you shoot those at a sample, particularly a certain frequency in your microwave at home, you can actually get, for example, water molecules to start rotating and vibrating. And because they have more motion, they have a higher temperature, and your food gets a little bit warmer because of that. So microwaves for molecular rotation levels. Infrared may be used to check out vibration levels. Infrared spectroscopy, you shoot infrared light at a sample, and the bonds inside the molecule start, bending and vibrating and moving around, and they produce peaks on a graph that you'll probably see if you ever take organic chemistry. You're going to be doing that a lot, trust me. And ultraviolet and visible, you get transitions in electronic energy levels. You've probably heard of or seen the atomic spectra, and that's what occurs when you add photons of these, mostly visible, but some ultraviolet and infrared. And you can get electrons to actually jump up to higher energy states inside the atom, and then they come back down, and when they come back down, they have to get rid of the energy you just gave them, and out comes these little colored photons. For example, in hydrogen, you get 4 different colors photons. 2 purples, a bluish green, and a red, and that's typical of hydrogen. And it's kind of nice to know that when you're seeing an atomic spectra, it's actually the little electrons shooting little photons at you as they go down to different energy levels. Okay, and we're also told that you can measure the energy of those waves. There's a couple of formulas on the equation sheet where relating the wavelength and frequency to the speed of light. C equals wavelength times frequency. So note how to use that one. And the energy of the photon is proportional to its frequency. So the higher the frequency, the higher the energy of that particular photon. And we're introduced to something called the photoelectric effect, which is what happens, say, in a solar panel, where if you take light of a certain minimum energy, and let's go back to our previous slide for just a second. And if you give electrons energy, they may jump up to higher energy states. But what if you get them all the way to the top and you give it more energy than it needs just to get to the top, you can actually get the electrons to escape the atom if you give it enough electricity or enough energy. And so the photoelectric effect is what happens when high energy photons hit a sample of matter and eject electrons out of it because you've now given them plenty of extra energy. And the electrons can then, because they're free electrons, can start to produce an electric current, which is kind of a neat thing. Okay, and because of that, there is another slide on the photoelectric effect. So take a moment and read that. If the frequency and energy of the light are too low, the electrons are not ejected from the atoms. They may jump up and jump back down and give you a spectrum, but they won't be ejected. And that's cool. And that gives us another form of spectroscopy that we're introduced to in this unit. And it's called photoelectron spectroscopy. All right, PES for short. And what happens is if you take a sample and just flood it with all kinds of energy and radiation and things, electrons from different shells can actually be ejected. And for example, the electrons from an s orbital might be ejected with a certain minimum amount of energy. The electrons in a p orbital might take a little bit less energy to be ejected. But you can measure the ejection of electrons and how many electrons are actually being given off. So if you take a look, for example, and you get these graphs that look like little peaks and numbers underneath them or nearby, showing the energy in megajoules it needs to remove electrons from different shells. Now, lithium has an electron configuration that's very simple: 1s2, 2s1, only 3 electrons. And if you look at a graph like this, there's a peak that's twice as tall as the other one, and it's at a higher energy, 6.26 megajoules. So that represents the 1s orbital with 2 electrons in it that were ejected at that energy. And then if you move to the next highest energy, this represents the 2s, and you'll see it's only half as tall as this one because there's only 1 electron in the 2s orbital. And they get more and more detailed. Every orbital would have a peak on a graph like this. So if there were 5 peaks on the graph, one would be the 1s, the 2s, the 2p, the 3s, and the 3p. And then you can tell by the height how many electrons are actually in them. So it's good evidence that electron configurations do exist, and we can kind of map them out. You might even see data that looks like this. So for hydrogen and helium, for example, they only have 1 orbital, and so there's only 1 energy at which those electrons are ejected. Lithium has 2, beryllium has 2, boron has 3, and by the time you get up to calcium, calcium has 6 different orbitals, all the way up to the 4s, and each one of those, as the higher you get in the orbital range, the less energy it takes to eject them. And so you might be asked to interpret data like this. One quick note, if helium and hydrogen both have only 1 orbital, why might it take more energy to remove helium's electrons and not hydrogen's? And you might be asked to compare those. Always think back to the nucleus, the thing that's holding the electrons in the atom to begin with. And helium, because it has 2 protons, is going to attract those electrons closer, and it'll take more energy to get them to escape. So more protons, higher ionization energy for those electrons. Believe it or not, guys, we only have one section left. And because we dealt with solutions and how light can interact with solutions, light can interact with ions to make the solution appear different colors. Nickel makes green solutions, copper makes bluish green solutions, cobalt, a lot of times red, and so on. And so because atoms and ions have color in the solution, we can actually measure the concentration of the solution using the color, and that's where Beer's-Lambert law comes in. Beer's law for short. Beer-Lambert law relates the absorption of light by a solution to 3 variables according to the equation. Absorption equals the molar absorptivity constant, the path length, and the concentration. And what happens is if you shine light through a sample using like a little cuvette like this, some of those ions may absorb some of those photons of light. And if you know how much you sent in and how much comes out. We have machines that do that for us, colorimeters, and we can actually then calculate how many of those ions are in there. We usually do this by creating a known set of standards of varying concentrations that we actually know, and we run them through our colorimeters, spectrometers, to see how much light these things absorb. And what happens is that ends up, if we do it right, being a linear relationship. This is what Beer's law tells us. It's a linear proportional relationship between the absorbance of a sample, how much it absorbs light, and the concentration in moles per liter. So if we have our known set of standards, and then we run an unknown, we don't know what it is, but we can compare it to the known standards and find its concentration using a graph or the equation for the graph. All right, it should be noticed, I was just asked this question. This equation, Beer's law equation, A equals EBC, does appear on the equations sheet for the AP Chemistry test. I can't recall actually seeing a calculation where you actually calculate you'd have to be given the molar absorptivity and the path length. But once you have those, it's really simple math to do, find the concentration from the absorbance or vice versa. And so I think that that's passed over and not included as an actual math question. But the concept is something you're likely to see, and that is that the absorbance is proportional to concentration. And so if you have some known standards, you can find your unknown concentration. Okay, so I will end with, again, a list of our topics from this unit. It was a lot. Sorry about that. But if you want more detail on any of those, you can head over to my playlist. I've got some completed already. I'll be working on some more. But yes, and if you have any questions for me, please send them in the comments or directly. And in the meantime, happy studying, happy solving, and good luck on the AP exam.